Okay, what we did last week, what we discussed last week, was how to complete hypothesis testing on one sample, on one population. And what is hypothesis testing? Well, it's a method, it's a test that we run in order to approximate the population parameter, a specific population parameter, whichever of the four that we learn to work with. And to approximate it, uh, using the method of the hypothesis testing, utilizing the CLT theorem. So basically, we can take any kind of distribution and consider a sampling distribution out of that distribution, and then use the normal distribution or the student distribution in order to run our tests. But the whole point is that last week we worked only with one population. So we were trying to approximate the specific parameter on one population. The difference, though, and what we will do this week, is to learn how to compare population parameters from two different populations. And this is something that comes up all the time in real life and in analysis, either in business, science, finance, engineering, everywhere. Many times we want to compare two different populations. What we want is to compare two diets and find out which diet gives us the best results. We want to compare two testing centers and find out which testing center does the better job with preparation for students. We want to compare two students. Assume that you are in the admission department of a university. What we have to do is basically take each one of those students and find out if each one of those students can fall in the confidence interval that the university has set of accepting the admission that the university has to offer, and at the same time be successful throughout the 4 years or the 2-year degree that that the applicant wants to complete. So everywhere, what we do is that we compare samples. Most of the times, we want to compare more than two samples, more than two populations. But this week, we will focus on two populations. Next week, we will learn how to handle situations where we have more than two populations. That is very similar. So, other times we compare proportions. Other times we compare the means, the averages, or the standard deviations. No matter what type of measures we want to compare, the methods that we follow are the same. They are a little bit different than the hypothesis test that we learned last week, and we will identify the differences. And of course, the formulas that we use in order to calculate the test statistics are different. The reason is that last week we were trying to calculate the test statistic, so basically to standardize the specific variable for the measure for a specific sample. This time, what we want to do this week is to standardize the difference of the two measures from the two different samples. So before we start, we want to make sure that we understand and we learn the vocabulary for this week. So we are going to be working, let's start with proportions. We are going to have two populations. and we are going to take a sample from each one of the populations. So we have the population proportion. That population proportion is something that we don't know, that we want to measure, we want to approximate, but basically we don't want to, the end result of our method is not going to approximate the P1, the population proportion for one of the populations, but to approximate the difference of the population proportions of the two different populations that we compare. N1 and N2 will be the size of the samples from the two populations. X1 and X2 will be the number of successes in each one of those samples. P1 hat will be the sample proportion for the first, and P2 hat will be for the second. And of course, Q1 and Q2 hat will be the 1 minus the P hats. I'm sorry. We also have to consider now a pooled sample proportion. What is a pooled sample proportion? The pooled sample proportion is a new proportion that is combining the sample proportions of the two samples that we work with. Why do we need to do that? Well, I'm sorry. The reason that we want to do that is that when we start comparing two populations, we do not require the two populations, the samples that we get from the two populations to have, for example, the same size. We don't require the two populations to have anything specific to be the same for both of them, so they can be similar. So when we come and we compare, let's say, the proportion in the one and the first sample and the proportion of the other sample, then it's as if we compare apples with oranges. And this cannot be done. So what we need to do is to consider a pooled sample proportion. That is the P bar, that is now a proportion that is received by the two samples combined. Now, what do you see here? On the numerator, we have x1 plus x2 that are the successes for the first and the second. And what do you see on the denominator? The sizes of the samples. So the entire sample 1 and then the entire sample 2. If you look at this fraction, what this fraction represents is as if you had taken the two samples from the two populations together and you put them together, you merge them. This is exactly what you do when you start the problem, because you cannot compare apples and oranges. What you do is that you put the samples together and you consider them as one whole sample. There are some requirements, though, in order to be sure that we are able to run the test. And the requirements are specific in order to be sure that we are able to actually draw the pooled sample proportion. And this is, first of all, that are coming from simple random samples. That is a regular requirement. We always require that. The other, though, is that the number of successes is at least 5, and the number of failures is also at least 5. What is the test statistic? As I said before, we are going to be working now with a different formula that will give us the test statistic to standardize the proportion. Okay, what you see on your screen right now is the test statistic for the two proportion test. What do you see? On the top, you see the difference of the p hats minus the difference of the p's. So you're taking the sample proportion and you subtract that, and then you take the hypothesized proportions for the populations and you subtract them. So what do we have? We have the difference of the differences. So the difference of the differences of the sample proportions and of the hypothesized proportions. As in the test statistic for the proportion that we learned last week, we had p hat minus p. Now we are looking at the differences. Now at the denominator, we have the square root of p bar times q bar over n1 plus p bar times q bar over n2. Similar to what we had last week, square root of p hat times q hat divided by n. There we had one sample. Now we have two samples. Instead of taking for each one of the samples the p hats and the q hats, we are taking the p bar and the q bar. And what is this? As I said before, this is going to be the pool sample proportion. In this way, we try to merge the samples and keep the test statistic the same as before. The p-values, they are going to be calculated either by R or any other type of technology as before. The confidence interval estimate for the difference of the proportions will be similar to what we had before. The difference is that instead of having the p hat minus the margin of error and p hat plus margin of error, now we have the difference of the proportions minus the margin of error. Okay, the margin of error is again the standard error that you see right here times the z-score for the alpha half, since we have a confidence level around the proportion. So we have a two-tailed confidence error. So, do people have indifferent spending habits depending on the type of money they have? So basically, do I spend the same amount of money if I have a $100 bill on my wallet than if I have 5 20s? That's the question. 89 undergraduates were randomly assigned to two groups and were given a choice of keeping the money or buying gum or mints. The claim is that money in large denominations, so if I have a $100 bill, is less likely to be spent relatively to an equivalent amount in many smaller denominations than if I had 5 20s. So we want to test this claim at a significance level of 0.05. What do I have now? I have two groups. So I have 89 different undergraduates, and I will divide them into two groups. I don't need to divide them to the same sample size. I can have 20 undergraduates in one group and 69 undergraduates in the other. So let's see what happens. In the first group, I have 46 undergraduates. In the second group, I have 43. 12 of them in the first group spent the money. 27 of them in the second group spent the money. The first group was given a big denomination. In the second group, we're given a small denomination. Now we have all our numbers to calculate the p hat and the p bar. The p hat is 12 over 46. The p2 hat is 27 over 43. The p bar now is taken by this formula and it's equal to 0.44, almost 0.44. So we have the first numbers in order to start calculating. We do the requirement check. First of all, they are randomly selected and they are randomly assigned to the two independent samples. I have 12 in the one and 34. I'm sorry, 12 in the first group that they were successes. So it's higher than 5. You remember the second requirement is that they're higher than 5. And 34 who did not. So this number is also higher than 5. The subjects given the quarters are 27 and 16. So all the numbers are higher than 5. The claim that money in large denominations is less likely to be spent. So what does this mean? This means that the group 1 the proportion, the percentage of people in group 1 that spent their money will be less than the proportion of the students in the second group that spent their money. So apparently, if you look at your numbers, the actual numbers is 12 over 46 and the other is 27 over 43. And these numbers that you have are actually telling you that the P1 hat is less than P2 hat. Now, what we want to understand is that does this specific test, the samples that we have and the numbers that we have, tell us that there is a significant difference here? So is it statistically significant, the difference that we have? So that's the claim. And the hypothesis, we write the hypothesis in the same way as we wrote the hypothesis last week. So P1 is equal to P2 or less or equal, greater or equal to P2. H1, P1 is less than P2. So the proportions are less, and the claim is going to be the alternative hypothesis right here. So what does this mean? Since this is my alternative hypothesis and this is my claim, this means that my test is going to be a left-tailed test. The significance level is alpha equals to 0.05. What does this mean? First of all, it means that since I have a left-tailed test, then the rejection region is going to be at the left tail, and it's going to have 5% area. So 5% of the total area of the bell curve will belong to the rejection area. So we have our numbers. We have the the pooled proportion and the Q bar, and we run the test. The first thing that we need to do is to calculate the test statistic. So we calculate the test statistic using the pool sample proportions here, and we get our result to be negative 3.49. So what is this? This is the z-score that corresponds to the difference P1 hat minus P2 hat. So if you take this difference and you assume that the difference of the two samples follow the normal distribution, then the corresponding z-score is negative 3.49. So what you need to do is find the p-value and compare it with the significance level. You can do it either by finding the p-value, or if you want, you can do it using the critical value. One of the two methods will work out fine. The p-value, the corresponding p-value for the negative 3.49 is going to be 0.0002. And this number is less than the significance level, that is 0.05. So apparently, this means that the z-score negative 3.49 lies on the pink area, right, on the left side of the bell curve, in the rejection area. So this means that we will reject our HO. Now, if you want to run the same test with a critical value, instead of calculating the p-value for the z-score, for the test statistic, what you're going to do is you will find the corresponding z-score for the alpha. The alpha was the 0.05. The z-score for the alpha is going to be negative 1.645. It's negative because we have a left tail test, so corresponds to this vertical line here that separates the rejection area from the acceptance area. And again, you compare now the z-score that you found, the test statistic, negative 3.49, with a negative 1.645, This number is smaller than that, so it belongs in the rejection area. So what does this mean? This simply means that we reject our null hypothesis. So after we reject the null hypothesis, what do we need to do? We need to go back and find out what's the relation between the null hypothesis and the claim. If you remember what we had before, the claim was that the P1 is less than P2. So the claim is the alternative hypothesis. So if I have to reject the null hypothesis, then this means that I have enough evidence to believe that the alternative hypothesis is correct. So there is sufficient evidence to support the alternative hypothesis, that is the claim, that people with money in large denominations are less likely to spend relative to people with smaller denominations. And this is the conclusion of the test. I want you to see again that the steps of the test are the same as we had last week. So the claim, the setup of the hypothesis 2, the significance level. The step 5 now is that we run the test. Before we run the test, you have to calculate the pool proportion. You calculate the test statistic, and then you decide using either the p-value or the critical value. That's the 7th step, actually, on the 8th step that I gave you as a framework last week. And the 8th step will be to actually conclude based on your claim. Nothing different than what you have done before. The only difference is that what you did is that you ran a test on the difference of the measures of the point estimates of the two samples. And you showed that you have enough evidence to support the claim. So there is a difference. So basically what you come back to say is that money in large denomination is less likely to be spent. Of course, all this with a confidence level of 95%. So what we want also to do now is to construct a confidence interval estimate of the difference between the two population proportions. This is also important. Confidence intervals are always what we want to have. Why? Because as we discussed last week, statistical significance is different than practical significance. When we work with practical significance, and we discussed a lot of different examples last week, we realized that we may have some statistical significance based on a specific percentage, but this doesn't mean that makes sense to take action when we have statistical significance. Why? Because basically what we do is we test and we look at our number and we see where the number is. Now, if I had two samples and the difference of the samples was giving me a test statistic that it was not negative 3.49, it was negative 1.665, then again the number would be in the rejection region. But the difference is so small right here and doesn't have any practical significance. I cannot trust this that much. The only thing that this would tell me is that I should consider a different confidence level, a different alpha. So that's why it is very important to construct confidence interval estimates for all my measures. Let's see how do we construct a 90% confidence interval estimate of the difference. I calculate, as I said before, the E, the margin of error. How do I do that? Well, I calculated using the p-hats. And as Advait asked why I don't use the pool proportions. Well, simply because right here I want to be accurate on my test using the statistical analysis tools, while when I create a confidence interval, I don't care, not I don't care, I want my confidence interval to be as inclusive as possible. So I want to be accurate based on my samples now. The margin of error that I get is 0.1613. I add this to the difference of the point estimates. I subtract it from the difference of point estimates. I add it here at the difference of point estimates, and I get my confidence interval to be this. Now, I want us to pay attention to this that says the confidence interval limits do not include 0. So as you can see, you get from a negative number to a negative number. So the difference is negative. What does this mean? This simply means that the P2 will always be bigger than P1 in the entire confidence interval. It will fall at the entire interval falls on the left side of the zero. So this means that the difference will be negative. No matter what, it will be negative. And a negative difference, it simply means that the P2 will always be smaller than P1. P2 is always greater than P1. That was the test for the two proportions. The way to calculate the difference of two proportions for two different populations is 1. When we come though to differentiate, to find the difference, if there is a difference, between two means, we have two different tests. And the reason for that is that we have two different situations that we want to compare the means. Sometimes we want to compare means of two populations that are independent. For example, I want to compare the cholesterol levels between females and males. The population of males, I take a sample from them. The population of females, I take a sample from them. I compare the cholesterol levels for the samples. In order to see that if in general the two populations have different cholesterols, if the one is smaller than the other in general. But it is possible that we can use a test in order to compare means of dependent samples. And what are dependent samples? Dependent samples are samples that are coming from populations that they have some type of relation. The association between the populations may be given based on some kind of interval, that it may come from different type of relations, different type of variables, such as time. So I'll give you an example. Assume that I want to compare two, if a testing center if a tutoring center at the university is doing a good job, if they prepare the students well for a test. In this example, if I have this type of situation, then the test that I will run will be on the same set of students. So I take 30 students before they go to the tutoring center, for a specific test, and I give them the test. Then I take the average score for the test. Then the students go to this testing center, to this tutoring center for, let's say, 3 months of courses. They take 3 months of courses, and then I consider their scores at the end of the 3 months, and I find again the average for their scores. In this situation, what I have is the same set of students, that there is a region that their scores have changed. The variable is the score tests results, the test scores. This is my variable. So the values of the test scores are the values for my variable. I have two of them. The test score before the tutoring that they have received, and the test score after they receive the tutoring. But there are factors that they connect those two populations. The populations are not the same because the populations are the test scores, but they have been received by the same students. So right here I have matched pairs. This is how we call them. I have dependent samples. So in general, dependent samples are samples that are coming from a population, and they have some kind of underlying factors that they remain the same. This type of test is very important, and many times I cannot run a test on independent samples, and I have to run tests on dependent samples. Now think back to the discussion question and remember that. Two samples are independent if the sample values selected from one population are not related with the other. Two samples are dependent if the sample values are paired. There is some kind of underlying way of connecting the two samples. That's exactly the same example that I gave you. Let's see a dependent sample example. Students of the author collected data consisting of the heights of husbands and the heights of their wives. 5 of those pairs are listed below. The data are dependent because each height of each husband is matched with the height for his wife. The notation is similar as before. The difference here is that I have a mean. I use the standard deviation, and I use the sample mean. The hypothesis test for the two means, when I use that with the t-score, I use the square root of the standard deviation for each one of the samples. It is possible, and sometimes I do it, I use the pool standard deviation. When I have independent samples, I don't use the pool standard deviation. When I have dependent samples, I use the pool standard deviation. Calculating the confidence interval is exactly the same. The method is exactly the same as before. Okay, let's say this example. Researchers conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. With a significance level of 0.01, we want to make the claim that blue enhances performance on a creative task. What I want you to see here is that blue and red background can be considered qualitative variables. And we find ways of quantifying those variables. The requirement check is, first of all, that the values of the two populations are unknown and they are assumed not equal, so they don't have the same standard deviation. The subject groups are independent, and both sample sizes exceed 30. We have the data. Red background, n is equal to 35. The point estimate is 3.39, so the mean of the sample is 3.39, and the standard deviation is 0.97. The blue background, they have their own measures. We have the claim, blue enhances performance on a creative task. What does this mean? This means that the mean for the group 1 is smaller than the mean for the group 2. If we want to set up the age, the pair of ages, the hypothesis, then the claim will become the alternative hypothesis. Again, we have a left tail test, while the null hypothesis will be M1 equals to M2 or M1 greater or equal to M2, mean 2, that is the same. Now, the significance level was, from what I remember, 0.01 and not 0.05. It seems that we changed it. I don't remember which one is the correct one. We'll see in the next slide. We calculated the statistic, just plugging in the values. And we find, the test statistic to be negative 2.979. Now we calculate the corresponding test statistic to be negative 2.441. We look at the t distribution, and we want to consider the degrees of freedom. The degrees of freedom will be 34. Now, going back here, you will see that the degrees of freedom will be the less than the smallest sample. Less than the smallest sample. We run the test, and the test statistic is smaller than the critical value, so we reject our answer, our HO, the null hypothesis. What does this mean? This simply means that the M1 is less than M2. So basically, we come up that we have sufficient evidence to support the claim that the red background group has a lower mean creativity score than the blue background group. So, yes, blue enhances creativity. In the same way, we can also construct a 98% confidence interval. We calculate the margin of error, and we subtract it from the difference of the means of the point estimates, and we add it to the difference of the point estimates. The result will be from negative 1.06 to negative 0.10. So we come here and we see that the difference again is negative. So this means that mu2 is going to be greater than mu1. So there is a significant difference between the two means, since the interval doesn't include the 0. Now, what I want us to do, because it's already 8:30, is to look at the dependent sample really quick, because there are few differences here. So let's look at the example directly. What do we have? We have matched pairs here. Do we have an explanation? No. We have matched pairs of heights of US presidents and heights of their main opponents. I'm pretty sure you have already heard about the claim that US presidents usually, the ones that they are elected, are taller than the opponents that they have. So we can test that. We can test that by getting the height of the president and the height of the main opponent. Right here we have a very small sample, but let's look at it. Since there is a relationship as a base for this matching pair, we look at the data and we assume we can see that they consist of dependent sampling. Why the samples are dependent here? Because they are pair matched. What do we have? We have pairs of president and opponent. So we are looking at two samples from two different populations. The populations are the population of presidents and the population of opponents, but they are matched. So there is a relation between each one of the sample data points for the first sample and for the second. One thing that I want to make sure that you understand is that whenever we have independent samples and we try to run a test on their means, then we don't need to have the same size samples. We can have different size samples. When though we run the hypothesis test for dependent samples, then we need to have the same size samples because they are paired. So here is the notation. D is the individual difference between the two values of a single matched pair. So the difference of the matched pair. Mu D is the mean value of the differences for the population of all matched pairs. D bar is the mean value of the differences for the paired sample data. Standard deviation of the differences for the paired sample data, and N is the number of pairs of sample data. N is going to be the same size for the two samples from the two populations. The requirements are satisfied. The number of pairs for our samples is larger than 30, or the pairs of values have differences that are from a population having a distribution that is approximately normal. So, what is the test statistic? The test statistic is going to be on the difference. So we have the D bar, that is the difference of the samples, minus the mu D, that is going to be the mean, the hypothesized mean of the differences of the pairs. Standard deviation of the difference of the pairs, and square root of n at a fraction, a denominator, that is the sample size. So we are looking at the Ds. We calculated this for each one of those, right? Always you consider which one your S1 and which one is your S2 sample, because you need to compare. You need to keep track of those, because some of the difference will be negative, right? Don't subtract whichever way. You have to have one way of considering the first and the second term. Then the requirement check is, first of all, that the number of the data points is 5, and you look at your claim. The claim is that the mu D is greater than 0. So the mean difference is greater than 0. This is what you assume. What does this mean? That the difference of the height of the president and the opponent is greater than 0. So basically, that the president, that the president is taller than the opponent. So since the MD is greater than 0, as Advait said, what we have is that this is your claim. This will become your alternative hypothesis, But this, since it is greater than 0, it means that we have a right tail test. Okay, so this means that the rejection region will be at the right side of the bell curve. Significance level is 0.05. Now, the summary statistics are d bar equals to 3.2, and the standard deviation is 11.4. So let me go back here, and let's look again at our numbers. The d bar is the mean value of the differences. So the d bar is the mean value of those numbers right here, is the average of those. And the standard deviation of the d, the SD, is the standard deviation of those values, the standard deviation of those differences. So by calculating the differences, as we see them right here, then you simply take the mean of those, and then you take the SD of those in R to calculate the standard deviation and the MD. I'm sorry. And to calculate, oops, where am I? To calculate the d bar, that is the mean, 3.2, and the standard deviation of the differences, that is 11.4. So then you take the test statistic d bar, that is the mean of the differences, minus the hypothesized, that is 0, and divided by the standard deviation of the sample, difference of the sample, divided by the square root of n, that is 5. Your t-score is 0.628. You have 5 different pairs, right? Each one of the samples has size 5. So your degrees of freedom will be 5 minus 1 equals 4. And you calculate here your p-value based on the t-score, 0.628. So 0.628 is the test statistic, and you find the p-value. The p-value, the corresponding p-value 0.282, is going to be a number that is bigger than 0.05. But remember, when you have a right tail test, what you need to do in order to calculate your p-value. The p-value is, this is the probability, 0.282. Your p-value is going to be, okay, so if you go back here now, this means that you should not reject the null hypothesis. So this means that you do not have enough evidence for the to support the claim, right? Because if you don't reject that, then this means basically that you should reject that. So this means that there is not sufficient evidence to support the claim that the population, the presidents are taller than their main opponents. Now, if you want to calculate the confidence interval, same situation, 90% confidence interval. The numbers that you calculate are the same. This should be times. D bar, remember, and this is important to remember here, when you calculate confidence interval, the confidence interval that you calculate are not on the means, are on the difference of the means. And since you have paired samples, you consider the D bar, that is the mean of the differences. So you subtract the margin of error from the mean of the differences, and you add the margin of error to the mean of the differences. The result will be negative 7.7 and 14.1. Now, as you can see, the interval that you see right here, it includes the number 0. So what does this mean? This means that the mean of the differences, it can be either smaller or bigger than 0. So this means that basically your confidence level is almost split, the confidence interval is almost split between presidents that they are taller than their opponents and presidents that they are shorter than their opponents.